Good morning, good afternoon, good evening to you all, ladies and gentlemen. Welcome to the WP2 Scientific Achievements presentation. My name is Nwamanya Ephraim and I work at NACRI as a food scientist. And I'm presenting this on behalf of the different contributors from IITA, CIRAD, CIAT, FSA, NRCRI, SIP, JHI, and INRA. For this presentation, we are going to give you an outline of this work that we have been doing. One is that we talk about the work plan for WP2 in period 3. 2, I'll be talking about the sensory characterization of quality traits, the main achievements vis-a-vis the relationship with WP1 results. Biophysical characterization of quality traits, specifically on the development of SOPs and the proof of concepts for new biochemical methods and rapid cooking tests. I will talk about the ontologies, specifically the databases that have been uploaded to BreedBase in period 3 on both sensory and biophysical data. And then finally, we're talking about the perspectives for period 4, and specifically perspectives in relation to sensory and biophysical characterizations and perspectives on ontologies. That is the summary work plan for WP2 for this period. These are different partner institutions working on sensory characterization, texture analysis, and biochemical analysis. The focus products are broad for all the RTB food crops that we are working on, and these products are at different levels of progress as far as WP2 is concerned. Specifically for the products highlighted in red, including EBA, boiled yam, and pounded yam at NRCRI, boiled yam, boiled plantain at INRA, pounded yam at Bowen, boiled sweet potato at JHI, acheke, pounded yam, and fried sweet potato at CNRA, and boiled plantain and fried plantain at GAGBAP. There's still more work that needs to be done on these products. For sensory characterization, given the COVID-19 situation, most of the activities on sensory characterization were referred to or postponed to period 4. However, some of the partner institutions such as NAR Uganda, NACRI Uganda, and FSA undertook some sensory characterizations during period 3. In particular, for sensory analysis, 8 SOPs were validated and 1 is in progress. These SOPs that were validated include the ones on boiled products such as sweet potato, cassava, and yam, pasty products such as matoke, pounded yam, fufu, and eba, and the granular product acheke. In the development of these SOPs, 3 rules were followed. 1, standardization of the samples, that is the process so that the process is the same for all samples, control of the testing temperature to avoid variability, and then harmonization of the rating scale, which would be relevant during statistical analysis. For sensory profiles of the RTB food products, 5 databases or datasets are already available on the RTB platform, including matoke, boiled cassava, boiled sweet potato, and boiled yam. In addition, a tutorial is available to check the performance of the panel and organize data for statistical analysis. So for example, for the work done on matoke, 32 cultivars were used and 12 attributes scored on a scale of 0 to 10. From this, the results that were observed was that we could easily differentiate between the well-appreciated clones or genotypes from the poorly appreciated clones or genotypes. Importantly, the replicates were very close, showing that the panels were well repeatable, while the characteristics such as intense in yellow, matoke aroma, smoothness, and moldability in local cultivars well defined the appreciation by the consumers. As such, Chibuzi, for example, was selected as one of the best in terms of consumer appreciation, while Narita performed poorly. Furthermore, preliminary results on correlating sensory descriptors with instrumental measurements have been done. In this case, it was observed that instrumental measurements are good for structured products such as boiled plantain by using penetrometry or compression tests, as you can see on this other curve, where another squared value of 0.8 was obtained for sensory firmness and puncture force. But Instrumental measurements would be poor for pasty products, so therefore other methods need to be developed, such as rheology, and also there is a need to understand that some of the structured products can be predicted using traits such as dry matter. On prediction of other sensory attributes, good prediction of sweetness by sugars was also seen in boiled plantain, and this shows that proofs of concept are needed to find biophysical predictors for texture, stickiness, smoothness, and moldability of some of these traits. For biophysical characterization, a number of SOPs have been developed for specific characteristics such as dry matter, free sugars, starch, amylose, PME activity, and cell wall composition. But in addition to that, a number of other SOPs are under development or in draft form, such as starch, amylose, pectin analysis, cell wall extraction for the different RTBs, beta amylase activity, and total polyphenols. On the side of the raw materials, SOPs for preparing raw materials such as boiled cassava and boiled yam are already in place. But also importantly is that there is progress on on some of these products, especially for extrusion at the different partner institutions. However, problems still occur where texturometer has not been received, for example, in NRCRI, CNRA, and SIP, and CABAP, and there is a need to help these groups to move forward. From biophysical characterization, it was also observed that actually diversity of processing ability and end product quality is usually observed among the different genotypes. And 3 examples of the results obtained do actually explain this. So these examples are texture and cooking ability of boiled yam, texture and cooking ability of boiled cassava, and the rating ability and quality traits fufu. For the texture and cooking ability of boiled yam, 5 genotypes in 2 locations were worked with, and these were taken through rheology, color, and biochemical analysis. And it was observed that actually the cooking time depends on the variety and harvest location. There were no significant correlations between cooking time and firmness after steaming, and firmness actually depended on the cooking type, whether you were steaming or boiling. A very important result in terms of differentiating the different genotypes. Biophysical characterization also was done for rating progression in different genotypes, and based on penetrometer data, rating ability was found to be genotype dependent, and this allowed the clustering of the different genotypes that were worked with into 3 broad groups: 1, slow rating, fast rating, and intermediate rating clones. And these clones, this method therefore can be used to select the best in terms of what is required during rating and in the preparation of food. Still on biophysical characterization, relationship between texture and sensory attributes was seen in a number of traits. So for example, sensory firmness was found to be positively correlated to puncture force on penetrometry. Hard to break as a sensory trait was found to be positively correlated to hardness on boiled cassava, while easy to chew was also negatively related to chewiness as measured by the penetrometer. Based on this work, one could easily differentiate between good and poor quality traits, where good quality traits would include, for example, softness, crumbly, and slightly sweet taste, while poor quality would be defined by traits such as bitter and hard to chew in the mouth. Moving to product proofs of concept, 3 proofs of concept have already been undertaken: 1 on water absorption for boiled cassava roots, effect of pectin and degree of pectin methylation on cooking quality, and cell wall characterization, starch properties, and enzyme activity of sweet potato genotypes. For the water absorption proof of concept, it was observed that water absorption at 30 minutes could easily predict cooking time and henceforth be used for screening cassava clones. Looking at the box plots on this curve, one can easily tell that the varieties could be ranked or differentiated between short cooking, medium cooking, and long cooking genotypes. And these are shown as above, but importantly, the short cooking genotypes also had high water absorption, while the long cooking type of the varieties had low water absorption. So therefore, cooking ability was inversely related to cooking time, and this result is very important, especially when screening for cassava. But importantly, diversity was also observed in the different clones used, and hence therefore one can easily select for what is required by consumers. On the effect of pectins and degree of pectin methylation on cooking quality of boiled cassava, it was observed that the firmness of boiled cassava increased with the level of the non-methylated pectins. This is a very important result because we understand that non-methylated pectins can easily form hydrogen bonds with other components of the root, increasing the firmness or increasing the texture or hardness properties of the root, henceforth determining whether the product will be firmer or harder than the other one. But important also in this case is the fact that a simple rapid extraction and pectin assessment procedure has been developed, and this will be used in estimating for the degree of methylation in the different clones. On sweet potato, still a number of genotypes were used to understand cooking behavior. However, from the studies, it was realized that no significant correlations occur between root composition and cooking time and firmness. We think that this is related to the fact that the samples used were inappropriate and the procedure also used was inappropriate. Therefore, more work is being done at JHI and SIP in Kenya, and another SOP is being prepared, and we hope to have better results on this in period 4. Still on cell wall characterization for cassava, yam, sweet potato, and plantain, it was observed that there are specific differences in the yield of cell wall material and pectins in the different clones. So specifically for work done at SIP within 15 genotypes, it was observed that the yield for cell wall material and pectins differed, showing diversity in these clones and hence possibility of selection for consumer preferred clones. On the ontologies, work has been done, and since in sensory analysis, about 74 variables for food product ontologies have been uploaded so far, and this will enable the breed bases to integrate these sensory trait measurements, and then maybe the breeders will be using them in future. But in addition to that, food product property dictionaries for matoke, boiled cassava, boiled sweet potato, and boiled yam have also been produced and have been uploaded on the RTB platform and are available on the breed bases. For biophysical characterization, 2 ontologies were developed and uploaded to cassava base, including one at Nakuri with 5 variables and one at SIAT with variables. These can be accessed, as you can see from these pictures here, where the uploaded ontologies are from the 2019 C2 set GWAS at Namronge and Serere, and in SIAT for the 9 variables for the 36 and 28 genotypes respectively. So that has been done. So looking at period 4, the perspectives for period 4 include the following. On texture analysis, there will be more work on developing and adapting while validating the SOPs for texture profile analysis. Developing new SOPs predict mealability or mealiness in the different RTBs, and also continuing collaboration among partners, especially on the subject of rheometry. For biophysical analysis, there is a need to finalize drafted and tentative SOPs for biophysical characterization of RTB crops and food crops. There is also need to collect biophysical data to expand the data sets of RTB crops and products, and also conduct a global quality assurance ring test for all the developed biophysical SOPs. For the proof of concepts, there is more work needed to develop SOPs for cooking time and water absorption, conduct product proof of concepts on the effect of polyphenols and polyphenoxidase, and continue to work on cell wall component starch characterization and enzymatic activities. For sensory analysis, there is more work needed in terms of understanding external preference or constructing external preference maps to identify the main quality attributes. But this also will go along with finalization of SOPs for preparation and sensory evaluation of the different products. And if this is done, then possibility of performing sensory evaluation will be a matter of making sure that people do the work, and then this will be followed by tutorials and the link between sensory and texture and biophysical data using appropriate statistical processing tools. On the databases, there is a need to develop by physical and textual databases using harmonized and approved SOPs. Develop sensory databases using harmonized and approved preparation and sensory SOPs, and also develop the ontologies. But importantly, on the ontologies is the realization that actually several partners have limited experience in formatting WP2 datasets, so therefore there's a need to support and train the partners on the process to ensure that quality data is uploaded. So already there is a strategy in place to do this, and this strategy involves the provision of training and support to RTBfood partners, formatting of the data according to RTBfoods templates, and also uploading to the RTBfoods website. So that's what we have for you from WP2. Thank you very much for listening in, and we hope that you give us comments that will make this work better and better in future. Thank you very much.